You've probably been there, right? You're driving along and boom, a ball rolls into the street or a car pulls out unexpectedly. Your foot just slams on that brake pedal instinctively. But what happens in that moment, well, it's not just about good brakes. It's this incredible dance with the laws of physics. And honestly, it's something most of us get totally wrong.
So let me ask you something. Let's say you're going 30 miles an hour. If you double your speed to 60, what do you think happens to the distance it takes to stop? Your gut probably says it just doubles too. I mean, that makes sense, right? Double the speed, double the distance. Well, hold on, because the actual physics tells a way more dramatic story.
Okay, so to really unpack this, we first need to be clear on what we even mean by stopping distance. Because, spoiler alert, it's not just about the car. It's actually a two-step process. And the first step happens right inside your head.
Yeah, the clock starts ticking the second your brain goes, "Whoa, I need to stop." And it doesn't stop until the car is completely motionless. That entire stretch of road you cover, from the thought to the final stop. That's the whole shebang. That's our stopping distance.
So we can split this whole thing into two main parts. First up, we've got the thinking phase. That's all about how fast your brain and body can react. And then you have the braking phase, which is all about the car doing its thing. To solve our little mystery, we've got to look at both of these pieces.
All right, let's kick things off with that first part, the thinking phase. And what's interesting here is that this piece of the puzzle, it's actually pretty simple. It really just boils down to your reaction time and some basic predictable math.
See, the math here is a straight line. It's super simple. If you go twice as fast, you travel twice as far before you even touch the brake pedal. It scales up perfectly. Double the speed, you double the thinking distance. Easy peasy, nice and predictable.
But, and this is a big but, that reaction time isn't always the same, is it? We all know this. If you're tired, if you've had a drink, or if you're, scrolling on your phone, your reaction time gets longer. And a longer reaction time means you're covering more ground, maybe a lot more ground, before your foot even moves. Okay, so that was the thinking phase. Simple enough. Now for part two, the braking phase. And this is where things get really interesting. This is where our common sense just completely breaks down, because we're not talking about reaction time anymore. We're talking about a head-on battle with pure, raw energy.
That energy, of course, is called kinetic energy. Basically, it's the energy of motion. The faster you go, the more of it you have. But take a close look at that formula. The most important part isn't the mass, it's the velocity. Why? Because it's squared. That tiny little 2 up there, that's the secret sauce. That's the key to this whole thing, and it has some seriously huge consequences.
So when you slam on the brakes, where does all that kinetic energy go? Well, your brakes have one job, to get rid of it. They do this through friction, which basically does work on the wheels. And all that energy of motion gets converted. It gets transformed into heat. You can think of your brakes as just really powerful heat generators, turning speed into warmth.
And just like your reaction time can change, your car's braking ability isn't always the same either. Things that make the brakes job harder, well, think about wet or icy roads, or maybe worn-out tires, anything that reduces that critical friction. Plus, a heavier car, say with extra passengers or a full trunk, has more kinetic energy to begin with, which means your brakes have to work a whole lot harder to get the job done.
Okay, we've looked at thinking distance, we've looked at braking distance. Now it's time to put it all together. This is the big reveal. This is where we see that dangerous speed multiplier in action and finally answer that question we started with.
And here it is. This is the absolute key. When you double your speed, your thinking distance, it doubles. Just like we said, nice and linear. But your braking distance, it doesn't double. It quadruples. It goes up by 4 times. And why? It all comes back to that little squared in the kinetic energy formula. You're giving your brakes 4 times the amount of energy to burn off.
Okay, enough with the theory. Let's put some actual numbers to this to see how crazy it gets. We'll take a pretty standard car, about 900 kilograms, and a driver who's paying attention, with a pretty quick reaction time of half a second.
So, at our starting speed, which is about 12 meters per second or roughly 27 miles an hour, the total stopping distance comes out to 38 meters. And you can see how that breaks down, 6 meters while the driver is thinking and 32 meters for the actual braking. Okay, so that's our baseline. Remember that number, 38 meters.
All right, now for the big moment. Let's just double the speed. We're now going 24 meters per second, or about 54 miles an hour. Now, if our intuition was right,
The new stopping distance should be double 38. So what, 76 meters? Let's find out.
Nope, not even close. The new total stopping distance is a whopping 142 meters. That is way more than double, and look where it comes from. The thinking distance did exactly what we expected. It doubled from 6 to 12 meters, but the braking distance, it exploded. It went from 32 meters all the way up to 130. There it is. That's the quadruple effect in the real world.
So let's just put those numbers together and let this sink in for a second. This gets to the very heart of why speed is so dangerous. This isn't someone's opinion or a safety campaign slogan. It's a fundamental law of physics.
I mean, just look at this chart. The visual says it all, doesn't it? We double the speed, but that second bar isn't twice as tall, it's almost 4 times taller. The space you need to stop your car doesn't just increase a little bit with speed, it absolutely balloons. So, look, if you only remember one thing from all of this, please let it be this right here. Your braking distance is proportional to the square of your velocity. That relationship between speed and braking distance isn't a gentle curve. It's a steep, unforgiving wall that you can't escape. It's just physics.
And at the end of the day, you just can't argue with that. The laws of physics are the laws of physics. They're not going to change for you. But what can you change? You can change the things that affect your reaction time, like putting your phone away. You can change your car's condition. And most importantly, you have total control over that one crucial variable, your speed. The physics might be fixed, but your choices aren't.